Okay. Good evening, everyone. My name is Fabian Catalan, and I work with Manuel Sponcos and Felicia Owens on the group project 2C, which consisted in obtaining values for flux ratios and mass estimations for some exoplanets in the HR X799 star. Okay. For a quick summary, we are going to explain a bit of the characteristics of the system, and then we're going to make a quick explanation on how we obtain the coordinates, flux, and masses. And finally, we are going to show some conclusions that were obtained through this work.
Okay, so let's talk about the star of this system. The HR 8799 is a star that is visible to the naked eye if we look at the sky. It belongs to the Pegasus, to the great square of Pegasus. And it's also 40.9 parsecs away from Earth, basically a 30 million year old star. And what's quite unique about it is that it's a gamma Doradus variable star. And specifically variable stars display variations in luminosity due to non-radial pulsations at their surface. On the right image, you can see the 4 planets that consist of the planet system. And specifically, we will talk about this one, the C and B. And it's also quite important to mention that these planets, along with Fomalhaut B, were the first exoplanets whose orbital motion was confirmed by direct imaging.
Well, as for the coordinates, the project consisted in obtaining some guess values for both exoplanets C and B. For that, we used DS9 as it enabled us to obtain a more precise determination of the coordinates. And with that, we measured the raw positions and brightness of the planets. And with performing some filtering to reduce some noise, we compute the CNR map, from which we obtained values higher than 5 for the signal-to-noise ratio, which means that these two objects can be considered with detections.
Now, when it comes to flux and mass calculation, we will not go into much detail about the code. Basically, we used these formulas, and the most important thing that we mentioned about the first one is that you need to take into consideration the calibration times, and if we didn't have taken them into consideration, we would totally have different results. And then we calculated the absolute magnitude of the star, and having calculated that, we managed to calculate its exoplanet's absolute magnitude, and then using the Ames-Cond model, we managed to calculate the masses. And let's compare them now. So as you can see, these are our results, and when we compare them with the best results that we had from Godzewski, we actually calculated a 25% percentage error for the inner planet. We were not quite satisfied with that result, but we could not improve it. But when it comes to the outer planet, we actually got a pretty good result with only 6.3 percentage error.
Well, and finally, for the question that was made in the project, well, we obtained that given the same absolute magnitude, the estimated mass of a planet changes over time. And as time passes, the object cools and its luminosity decreases. And to maintain the same level of brightness, the estimated mass of the planet must be higher. For example, the inner planet with an estimated mass of 7 Jupiter masses at a younger age changes to a value close to 12 Jupiter masses at 80 million years, which is in accordance with the Ames-Cond model, which correctly predicts that as an object's age, the luminosity maintenance must correspond to a higher mass.
Thank you for your time.
Thank you for your time.
Hi, this is Jason. Do I go up here or? Okay. This is really cool, really great. You guys, got some really precise masses. I was wondering if you had thought about what you could do in the future to maybe improve. You said you looked into trying to improve your mass estimates and comparing them to the literature. What have you thought about ideas to maybe make your masses a little bit more precise or more accurate?
Basically, we use the scripts that we had from the Jupyter notebooks, and most of them were basically rough estimations. So if we could use more precise calculations, we could have gotten better results, we believe.
Great, but you guys got really close already, like 10% error on the math, so nice job.
Yeah, but when it comes to the inner planet, we got 25, so yeah, we were not satisfied with that one.
Time to start working on a research project.
Okay, thank you. Can group 2 come down, please? Yeah, let me get the other mic.
So when we're doing the feedback and questions for group 2, I want group 3 to line up. Let's just always line up during the question time.
All right, so here's the mic.
Oh, here's the mic, okay, yeah. Oh, there's a timer. Okay.
This is forward, back, and the pointer.
Oh, okay.
All go to the center so that people online can see you.
Oh, yeah, actually true. I don't be shy, come on. So group 2, we are working on estimating the planet mass, and then I mean, of course, we have to introduce ourselves. I'm Alexis Lau. I'm from Laboratoire d'Astrophysique de Marseille, LAM.
I'm Sonia Choi from the University of Arizona. I'm Jialing Ko from University of Arizona. I'm Nihadushinda Kumar from Penn State.
Nikolai here from LAM, also Marseille.
I'm Yasser Lukai from University of Finland.
So basically the questions to answer basically is that we need to estimate the mass. From estimating the mass, we actually need to get the calibrated flux ratio. And then to do that, we are using Jupyter Notebook. And there was a bonus question, basically, saying that like what will happen to the mass if we estimate the age is 2 times older and 2 times younger. So basically what happened is like, okay, just a little bit brief intro of HR 8799, our favorite system by far, because a lot of people study that. And this data set was observed with KEGG in 2009 in L prime age, actually depending who you're asking, because different literature suggests different answer based on the fact that some believe that they might belong to one association and some might believe that they were in another moving group. Therefore, there was a huge discrepancy in the age estimation. And then for us, we are using the age estimated by this paper Bandit in 2021. So with 42 million years with like plus or minus 16 error bars. Yeah, there are 4 planets. It's called A, B, C, D, and E.
So quickly, we need 2 points. The first part of the project is try to get the flux of the companion. So for that, we use the residual image. We feed that to the Gaussian, and we have our raw flux. So since we are using the post-processing, we need to correct by the flux that we are losing because of that. And for that, we compute the throughput. That is basically we inject fake planets and different position angles, but at the same separation from the planet that we're interested in. For example, that one, right? Yes, that one that we injected. So in principle, this works. And to obtain the flux radio, we choose that formula, and we need to divide by the stellar flux to have the contrast flux, basically. And the second part is get the mass. So we have our flux ratio, and we need to convert to the absolute magnitude. So for that, we need the magnitude of the star, the distance, and of course the flux that we measure. And then we need to use these evolutionary models that is basically know how our planet is evolving time, and some of the physical parameters change in time also. And here we are using the EMSCON from the Barafi et al. And here an example in the y-axis, the absolute magnitude versus the mass, and the difference in isochrones depending on the age. So in principle, it could be easy if we have the age at the absolute magnitude, because with that we can get the mass. And the first planet.
So for planet, no, that's fine. For planet B, I basically followed what we were taught in the hands-on session, which, oh no, yeah, just point at that, yeah. So which I took notes during the hands-on session and drew that on my iPad. So we learned that by injecting a pair of fake planets at 90 degree separation, we can get the throughput and the flux ratio of the real planet. And planet B is our outermost planet. And we got those values, and we got the mass of the outermost planet is 6.8 Jupiter masses. And that's the plot that Nico generated showing the mass and like the error bars and how it changes as a function of number of years, I guess, yeah.
Okay, so the planet sits at the upper right corner, and then so we inject 2 fake planets at each time, and we can get the throughput. And then the average throughput we got is around 0.5, and then this can allow us to get the flux ratio around 1.6 times to 10 to the negative 4, and then we can get the planet mass around 9 Jupiter mass with an uncertainty of 2 Jupiter mass.
Okay, so I did the planet D, and it's just the same method that I use as others use. So the magnitude was the absolute magnitude was about 11, and the mass was about 10 mass of Jupiters. I think we're running out of time.
There's one more planet, okay? I'm sorry. Okay.
So for planet E, it's the innermost planet, so we expect to see a lot more noise and speckles, and we're trying to answer the question of if we increase the number of fake planets that we injected into the system, does it improve the mass recovery? The answer is no. From our data, it seems like both the throughput and the flux ratio did not improve with the increasing amount of fake planets that we injected, and therefore the mass estimation did not get better.
Here's just a summary table, like a masses from like the literature. This is our estimation. In general, some are basically is with a, yeah, not too bad, like of an agreement. So yes, success. And of course, it ain't much, but it's honest work.
That was some really cool plots, by the way. I really like the one with the fake planets going around in the circle. That was, and the mass and the evolutionary tracks, like plotting all the evolutionary tracks. Very cool. It looked like you injected a lot of fake planets for some of them, and not as much for the other ones. For the ones that you injected a lot, did you look into the uncertainties on the flux measurement and how that affects your mass estimate?
Well, sorry. We inject different planets,
Yeah.
because we don't know the effect in that specific position.
Yeah.
So we have indeed in the throughput, depending of the angle, a dispersion. So we can take that dispersion and propagate it in the mass at the end.
Yeah.
So that gives us like an idea of the uncertainty, but of course that is not the only source for the uncertainty.
I was just wondering, you folded that into your mass error bars you quoted at the very end.
Yes, but it's too small in the magnitude.
Nice.
What is dominating is the age at the end.
Nice. Cool. Ready, you guys are ready to write a paper, I think.
Hi everyone, we're going to be talking about the same system, so I hope you're not too tired of it yet. Real quick, this is our team. I'm Laura. Everyone can introduce themselves as they come up. You see them coming. Again,
again, going through this pretty quick because groups 1 and 2 did a great job introducing the system. But we'll be using Keck NearCam observations from 2009, 2021, just comparing those two epochs. The system has 4 known planets. Just keep note that planet B is outermost, and then moving in, we go to planet E at the innermost. And our question here is, does the SNR differ between epochs? And we'll also be, this isn't on the slide, we'll also be talking a little bit about the orbits. And if so, why does it differ?
Okay, so here are our 2 observations, or 2 images after we've subtracted the PSF. Here are the 4 planets, which you can pretty easily see by eye. It's easier to see in 2021. If you remember, the next thing we did was we cross-correlated the like a double Gaussian, like a 2D Gaussian with each of these. One thing I do want to point out is in the 2009 data, there's this bright speckle here in the center we think it's messing with planet E. So just keep that in mind. And then this is the SNR map. And the SNR that we're taking for our points is just the height of this map. And again, here are the points.
So we calculated the signal-to-noise ratio for planets of data of 2009 and 2021. And as we can see, SNR in 2009 for most of the planets was better, but except for planet E, but that we think probably it was because planet E was closer to the mask and the residual speckle. That's why we don't have a good SNR for that.
So now the question is, why did the signal-to-noise ratio change? There's several parameters that we studied. The first, most obvious one is the exposure time. So in 2009, the exposure time was longer, hence the larger signal-to-noise ratio. But there's also other parameters, such as the parallactic angle. So as you can see, in the 2009 sample, we've sampled more of the parallactic angle because the observation was done over 2 nights. So this might have contributed as well as to why we have a better signal-to-noise ratio. And the last parameter is just the weather. Even though we have AO, nothing is perfect, so bad weather can have an impact.
So we also kind of partially did a trace of the orbits of the 4 planets in regard of the both epochs, and I figured that they following the same pattern, which is like kind of consistent with the direct image from the both epochs. And interestingly, the planet E is having around like 80 milli-arcseconds change of separation. So here we have a conclusion. So first, like 2009 has slightly higher SNR. So the answer for this is probably like due to the exposure time, because it has a longer exposure time in 2009, and it's maybe the weather, because weather may verify your observation plan, and then the other parameters may change. So the second one is the planet E has a higher SNR. This is due to, it's very close to the max due to the coronagraph in 2009, and it's also near the speckle. So it's moving out based on the spinning from the mask in 2021. This is why it has a different pattern compared with the other 3 planets. And also it's a fast moving planet in frame because it has more significant angular and PA change. And that's just the end.
Nice, very comprehensive analysis. Yeah, it's actually very interesting to think. Like, have you looked at the images? When you looked at the images and you first did the reductions, which epoch did you think was better before you computed the SNRs?
I think it was like 2021 probably. It seems like it should be better, especially because of like Planet E. It's definitely easier to pull out Planet E from the 2021 data.
Yeah, for sure. I think sometimes, we have to be careful with our metrics, so sometimes we compute them, but maybe there are some errors in the assumptions we make. So if it's like by eye, it looks clear like one epoch is better, maybe the code I gave you isn't the best for computing SNR. Anyways, that was a really comprehensive analysis, and even including some orbit fitting. And I didn't appreciate actually that in 2021 E was actually further out, and that partially made it easier to detect. So nice investigative work there.
Okay, hi everyone. Our group explored how to make PyClip work for you by changing different parameters of the contrast curve. And as we each present a slide, we'll introduce ourselves, our affiliation, and whether or not we've used PyClip before. So I'm Rachel Bounds-Rubin. I'm from UC Santa Cruz, and I've barely used PyClip before.
Hi, my name is Eden McEwen. I am a second year at the University of Arizona in a grad program, and I have never even thought about using PyClip before. It's not my slide though, sorry.
I'm Sam Walker. I'm going into my 4th year of the grad program at the University of Hawaii, and I've never used PyClip before, and this is my slide. So I worked on varying the movement parameter, which basically governs how much rotation on this guy is allowed to occur before you start considering that PSF as a separate PSF for image subtraction. So in the tutorial, we used a movement parameter of 1. As you can see, I've varied it between these different values here. And so you can see that with movement of 0, you get more, what appears to be better contrast further in, but that's really because we're just more aggressively self-subtracting the planet signal. It's not necessarily better performance, and then you can see it as it goes further out, it sort of plateaus, and then as you get to higher movement values, you do less self-subtraction, and you end up doing worse later as further out as you get to movement of 10, and that's because further away in movement means further away in time, which means that the PSFs have had more time to evolve, which makes them more different, and thus you can't do quite as good image subtraction.
So I looked at the annuli parameter. So the annuli parameter is how much you're breaking up in rings from your center of your star. So in one annuli, you're not breaking it up at all. It's one big chunk. If you're doing 2, you have 2 rings, etc. So you can see here that it didn't really change a lot, probably because I didn't understand the parameter when I ran this, and it took 30 minutes, and by that point we were done. But I've been told by people who do use PyClip all the time that if you're doing something where you expect there to be different noise throughout your image, you want more annuli. So you want to be able to determine differences between close in versus far out. If you're doing something like a disk, you probably want something like an annuli of 1. An annuli of 20 is overdoing it, and it's just going to make things run very slowly, like maybe 30 minutes. Also, there are going to be artifacts as you split up your image into different rings. So a thing to consider that is not really shown here, but the more you split it up, the more you're going to have edge effects between the different annuli as you're doing the processing. So here we did 1 through 20, and then 10 seems to be about right. It didn't really change much, and we didn't have a lot of time to explore this.
Hi, I'm Macarena Vega from University of Rome Tor Vergata. So, no, sorry. No. So I look into the KL modes, which are the principal components, the number of principal components used to estimate and construct the stellar PSF and also the speckle noise. And we use from 1 to 50 KL modes as the web page in the documentation suggests for planets. And we found that, well, for large number of principal component coefficients, the contrast doesn't change as much, but of course for a small number of KL, the contrast is way worse. What we were surprised about is that for inner planets, like smaller separations, the best contrast is reached with a high number of PCs, And for large separations, then the optimal modes are 20, the red line. And that we were surprised because usually you expect it to be like the other way around. I guess that's also my slide, sorry. And here the images we got with all the number of Gale modes. As you can see in the first one with one mode, you have a lot of light. And also in the outermost planet, you see it like kind of blurry, and you see that's improved as you increase the number of Gale modes.
Hi, my name is Amber, and I'm a fourth-year undergrad at UC Irvine. Yeah, I've never used PyClip before. I also don't do direct imaging. This is all new to me. But since we're like out of time, I'll just do this really quickly. This is the version that we had in the tutorial. I think we had like num basis of 30, annuli 11, and what's the other one? Movement of 1. Movement of 1. And so we've just taken all of our optimal numbers and changed it to those, and this is what it looks like, and I think that it does look better. So, yay! Thank you.
Wow, very, very thorough exploration of parameter space. I was wondering if you had to improve things, like what would you improve? Like if you had more time to do this than just 2 hours, what would you do more in this?
I asked Jason what to do to make like PyClip correct, and he said that the answer is always to inject more fake planets.
That is correct. That is the correct answer. Good job, guys.
You learned well.
Okay. This is you guys. Oh, let me go back here. Okay. So forward, back, pointer, microphone.
Anyway. So hi everyone. So we did the orbit fitting group project. Click. So yeah, I mean this celebrity doesn't need any introduction. So click once again.
Let me just fix this.
Oh, introduce yourselves. Oh yeah. So I'm Giel, by the way. I'm from Leiden Observatory, a second-year PhD student. And this is?
Yeah, I am Maël. I work in Paris, and I'm a first-year PhD student. And I never read about orbitals before.
Hi, I'm Danielle Bovee. I'm a graduate student at the University of Texas, San Antonio.
Hi, I'm Ikram. I'm a postdoc at Washington University in St. Louis.
Hi, I'm Pongyi. I'm a PhD student from the University of Edinburgh and Leiden University.
I'm Rochelle, and I'm also a first-year graduate student at Leiden Observatory.
Maybe like a little bit like what we did. So we have the 4 planets, and for each planet, basically what you do is you extract the position, like we did in the hands-on session. So you measure the separation and the position angle. And you do this at 2 different times, 2009 and 2021. And then you basically take those numbers, feed it into a CSV file, and then you can like put that, you give it to Orbitize, and that does all the magic for you. And we did it for all the 4 planets. And so this is the first one, the B, so the most outer planet. So we used the numbers from Wang et al. At 2018 to compare. We also used their total mass and parallactic angle. And we see that we have like a semi-major axis of like 75 AU, plus minus like quite big numbers, but still matches kind of well with the paper, and similar conclusions I think for the eccentricity and the inclination, within like a good margin of each other. So the next one.
Yeah, so basically it's a bit of the same thing for every planets, because you just change which range that you take for the orbit fitting. And basically, we are quite near the wrong eternal paper values every time, but like the fit show less constraint values, and yeah, so we basically have wider orbit ranges for every fit.
Okay, so this is planet D. As you can see from the semi-major axis, they are actually quite close to each other. Also, you have to consider the plus and minus uncertainties here. As you can see, semi-major axis 30, but it's plus 10 and minus 4. So the uncertainties are quite large, but they kind of agree with each other with the original paper. We can say the same for the eccentricity and also for the inclination of planet D. Or I can continue.
And this is the orbital fitting results for the innermost planet E. So for this one, we found some weird results. So most of the orbits that they have a semi-major axis agrees with the value report in one at all 2018's paper. But then we also have found solutions that shows well, we use the laser.
Okay, sorry. There you go.
Yeah, these are the weird orbit we found, and we think it's mathematically possible, and this is and this prefers a high inclination for the orbit. But I think we only have 2 epochs of this orbit, so that's the best we can get.
Okay, here's the final orbital configuration that we get by using only 2 epochs for each planet. That's why we have this very high uncertainties, of course. And on the right, you can see the original orbital configuration with some portion of the random orbits that they had in the paper. So on the left, this is our orbital configuration. You can see these white circles as their positions in the images. And these are the full orbits. And in the red, I hope you can see as red, is the time epoch between the 2 images. So at least I think to some degree our results looks quite comparable with the original work. Thank you.
Very nice. That crazy orbit is a feature. It's allowed from just 2 epochs. That's why you need more than 2 epochs sometimes to tell. When you combine all 4 of the orbits solutions together, how did you pick what orbit to plot there? Like, is it some random orbit you found, or did you pick specific ones that are good, or like how did you? How do you drew?
Okay, so the final orbit, when we drove all 4, were actually from the median values of the semi-major axis, eccentricity, inclination, and all the angles and so on. So these are the median values.
Gotcha. Just as a warning, sometimes the median value of all your orbital parameters is not a valid orbit. But I think this time it is, but it's not necessarily true. So just be careful about that.
Okay, thanks.
Yeah. Great. Nice.
Hi, everyone. I am Jorge.
I'm Austin.
And I'm Anna from the Observatoire de la Côte d'Azur in France.
And this is our project. Oh. Technical difficulties. Yeah. So stop me if you've heard about this planet system before. Yeah, in case you haven't, this is the 8799 system, pretty canonical directly imaged system, bright main sequence star, observations with some of the biggest telescopes in the world. Here's some facts about the planets that you've heard about from other groups, as well as there's also a known debris disk that's been imaged and taken spectra by Spitzer and other observatories. So yeah, you want to go ahead?
Yeah, and so here are the science frames from, looks like the
years got messed up there. Here's the science frames from the 2009 and 2021 epochs. So fully reduced, but have not had their PSFs subtracted yet. So yeah, we used the PSF subtraction algorithm from PyClip, and used the PCA-based method. We didn't change any of the parameters between the two epochs. Yeah. Yeah, there's that. All right. And then.
So we have the residual output from PyClub for each year in 2009 and 2021 with the PSF subtracted. So after processing, we have the signal-to-noise ratio maps, and we can compare the result for each planet. Sorry. So for the planet B, we have 9.9 and 8.6 for the planet. Oh wow! For the planet C, 8.6 and 7.8. And for the planet D is almost 6.7 for each. So how we can see the results are quite close, but the main difference is on the planet E. So we have 2.9 for the observatory in 2009 and 5.0 in 2021.
As the other group pointed out as well, there are subtle differences between the SNRs for each planet between epochs, but one of the things that we found the most poignant was that the SNR for planet E, sort of between 2009 and 2021, went above that 5 sigma threshold for detection. And so one of the reasons we think that might be the case is because when looking at the first and last frames between the 2009 and 2021 epoch, the 2021 epoch underwent more field rotation between the first and last frames. So we think that might have helped with really distinguishing between astrophysical objects like planets in an orbit versus speckles that are on the detector. And we also just wanted to point out this sort of shows the importance of getting multi-epoch observations for systems and how you can use those different observations to learn more about whatever you're studying. And here's a fun little drawing of a HR799 system, and now he's smiling because he was detected above 5 sigma. So yeah, I think that's it. Thank you.
Nice. I'm gonna ask you the same question as the other group. When you looked at the images by eye before you computed the signals noises, which epoch did you think looked better, and did it match what your signals noise estimates give you?
Yeah, I would have thought it was the 2021 ones, but then obviously that wasn't the case after calculating. Yeah.
Yeah, I think probably needs a little bit more investigation to see if your eye is more trustworthy or is the algorithm more trustworthy.
Yeah,
it's one of those challenges. Yeah, good job. Thanks.
Thanks.
Maybe we should start over there. Just introduce yourself.
Hello everyone. We are a group. We are working on the orbit fitting, and I will start with introducing ourselves. My name is Chen Yang from Tsinghua University, and
hello everyone. I'm Mariam Savarbal from University of Liège.
Hi, I'm Zano from California State Northridge.
Hi, I'm Xian from Tsinghua University.
I'm Alex. I'm at the University of Southern Queensland in Australia.
And I'm Tina. I'm third-year PhD student from KU Leuven. And so we did a project about tracing out the orbits of the planets around HR 8799. Okay. The systems on the right, And we got 2 epochs of Keck data for the system, one from 2009 and one from 2021. And then our science question was, well, what are the orbital elements of the 4 planets? More specifically, what is their semi-major axis, eccentricity, and inclination? So in order to find this, we used PyClip first to analyze the images with angular differential imaging, where we used 30 principal components. So you can see the result of that at the images on the right. So above is the one from 2009, and then the lower one is from 2021. And then we used a 2-dimensional Gaussian to fit to each of the sources to find their raw position measurements, and we used these position measurements for orbitize, where we then try to find potential orbits for the planets. So we had to assume some parameters to resolve some of the degeneracies between the total mass of the system, the parallax, and the semi-major axis. So we assumed 1.52 solar masses from Wang 2018 for the total mass, and a parallax of 24.46 from milliarcseconds from Gaia DR3. And then we generated 1,000 orbits for each of the planets.
Okay, so each of us fitted the orbits of each of the planets independently. So this is for B, which is the outermost planet, and as you can see over the 10-ish years of observations, there's not very much orbital motion. So the posteriors for the orbital parameters are pretty poorly constrained, but the orbit, as you can see, is like reasonably consistent with it being circular. Here we are plotting the histograms of the posteriors, so we're also comparing in green the literature values from Jason Wong's paper, and in red we have the medians from our orbital fits. So for B, the parameters are pretty generally uncertain, but they're consistent overall with the literature values. We have the same for C, which is the next innermost planet, and the posteriors are again like very much consistent but less certain. For D, here we can see that there's like larger motion in position angles, so that we're observing a larger fraction of the orbital arc. So the uncertainties are gradually improving as we go closer in. And this is for E, which is of course the closest known planet. And the posteriors are like generally quite well constrained. We can see the eccentricity is very much favored to be low. You will note, if I can use the pointer. Yep. There we go. Oops. Come on. There we go. Okay, so there are some solutions for the orbital inclination that are the opposite to the rest, and the reason for that is that, come on, I'm like taming a tiger here. So for the 2009 epoch is here and the 2021 epoch is here. So generally the most preferred orbital solutions have the planet going this way around, but there are in fact some where it goes this way around. So this is some of the tribulations of only working with 2 epochs.
Oh, thank you. So in conclusion, we can say that Orbitize is great and it's easy to use. Results seems to be consistent and most of the time with the literature, and we can see clearly some better constraints at low separation. That's because at low separation the planet is able to move more, so we can constrain this in a better orbit, and this would be like reflected in how in the estimation of the parameters. Thank you.
Well, very nice figures. I also like your cartoon that you drew. That was very nice. When you were, how did you figure out that there was this second population of things that were going in the opposite direction? Like, what made you figure out that, you know, it was going counterclockwise or clockwise instead of counterclockwise?
I do orbit fitting for my research, so I just kind of knew.
I was like, very few people know that I of greater than 90 means counterclockwise and I less than 90 means counterclockwise orbits, visual orbits. So I was very impressed.
Thank you.
Okay, hi everybody. My name is Emily LaFleche. I'm a fourth-year PhD student at Purdue University.
I'm Evan Sneed. I'm a second-year PhD student at the University of California, Riverside.
I'm Cameron Mullen. I'm a second-year master's student at the University of Victoria.
I'm Vasudha Trehan, and I'm a second-year PhD student at SUNY Albany.
And today we're going to be presenting to you the results of our work on Project 3A, which is the Time Allocation Optimization Project. Thanks. So in this scenario, we have given ourselves this particular story. The year is 2050, and we've only been given 1 year of time with HWO to observe 164 target stars. This seems like a whole lot. So how do we go about deciding which of these particular targets to give observation time to? And furthermore, how much time do we actually allocate to each of these targets? And in this case, we are assuming a signal-to-noise ratio of 5 and a 10% overhead rate. Oh, thank you. So to recall a couple of key definitions, these are all parameters that we care a whole lot about when we're talking about this. We have completeness, which is the probability of detecting a planet from a given population about a given target star with a given instrument. So there are a lot of givens in this scenario. Integration or exposure time is the length of time the sensor gathers and accumulates a signal, and delta mag, which is the difference in brightness between the planet and the star, also known as the flux ratio. And if these don't tend to make a whole lot of sense to you, because I am also not a direct imaging person, this is the way that I like to think about it in terms of Taylor Swift. So if you were trying to acquire tickets to something like, say, the Eras Tour, and it's incredibly difficult to do this, then you may end up having to wait in a very long line, which could in fact be Ticketmaster's fault, but this can be sort of an analogy for integration time. And delta mag would kind of be like that parameter that affects how close you are to your star in this case, which is a pop star, but you know, obviously we can use a little bit of creative liberty here. So this might help you with understanding these very important parameters.
All right, so we have all these parameters. We have to figure out how we're actually going to try to sort through these parameters in order to make sure we do the science that we want to do. So we identified two really types of classes, the way we could schedule this. So we could integrate over every target star in our catalog to make sure we get to the same delta mag. And so there are some uses of this. It helps produce a uniform survey. And it's easier to determine the bounds on the existence of exoplanets regardless of the type of star, and so across the data set. And then there's this other set of this other class where we choose the integration times on every target star to determine a different delta mag. And that's supposed to be the maximum we can get for that star based off of the amount of time we have given. So the benefits of this is that the time spent on very dim targets is minimized, and we instead can spend that on really bright stars. And we can dynamically reallocate time as we're going through our system, going through our target list, to go back and try to spend more time on planet-star systems that we have candidate discoveries. So in order to do this, we programmed Yogurt into our code. No, I'm joking. We did altruistic yield optimization, which is a procedure that was developed by Stark et al. 2014. So we have an initial priority that's decided by ranking the stars in decreasing order of their completeness based off of at a certain time divided by that amount of time that's required to get to that completeness. We remove all exposure time from the lowest priority star. We use that new open time and reassign it to stars that will get the best change in completeness with that new change in time. And so that sets up just a giant for loop. You just keep kicking out stars and reallocating that time to other stars to try to make sure that you get the most total completeness possible.
All right, so here's a demonstration of our results. We're showing the different allocated times as a distribution of how many targets got what amount of time. So as you can see, there are some targets that needed a lot more time, but a fair number of them weren't eating up too much time. These are probably brighter targets that were given higher priority. After doing this allocation, we found that 84 of the 164 targets were left, so a bunch of stars that were just too dim and require more time than the remaining available time got kicked out of our survey. If we wanted to see all of the stars or take up all of the time, we would need to have designed this differently. So in this case, we saw 84 out of the 164, and this used up about 63% of the year because every remaining star was just too faint and would have taken more than the remaining amount of time in the year to observe. So here we're just doing a projection on the sky of our targets to get sort of a visual representation of what we had before from the notebook and the workshop, and then afterwards, once we do the time allocation, as you can see, there's less targets on the sky, but their completeness values are higher. We've got these sort of brighter colors. So as you can see, even though we have less targets, we have a better chance of finding planets around them. And so next what we wanted to do was see how would this change if we change the max SNR from 5 to 25, since 25 is a value that is cited as a good SNR for finding exo-Earths. And so here, by changing that SNR, we again are viewing even less targets now, but they get even more time allocated to them. We also use up more of the time in the year, so it's maybe arguably more time efficient, and we get better completeness values for them.
So in conclusion, there is a lot we can do from exoplanet yield modeling. Like a person like me who was just using the model data until now is learning how to model the data today. So example like which targets are higher priority and how we can decide what higher priority is, and then designing an observation based on program goals. So with more targets or higher signal to noise ratio, sorry. So in the future, we are planning to look at the change inner variable angle or outer variable angle values which influence the telescope design, and then modify habitable zone limits based on stellar parameters based upon the Ravi's paper. It's a nice paper. If you have not read it, you should read it. And identify completeness values for different star classes, and then plotting and comparing completeness curves for these modifications.
All right, and we would just like to thank the organizers of this workshop, as well as Google Gemini and Stack Overflow, the Power of Friendship, and the pool at the hotel, which was instrumental in giving us some energy back. We would also like to say no thank you to the Wi-Fi and cell signal, as well as our sleep schedules. So thank you so much for listening.
Great presentation. Thank you. I appreciated your, I'm over here.
Oh, hi, sorry, I didn't know where I was looking.
I appreciated your analogy at the beginning to try and make integration time and delta magnitude more tactile to us. Thank you, a very clear program presentation. I appreciated that you tried to implement AYO. I missed what you used as your Tmax in your implementation.
So the maximum total time set was 1 year. That was what we were provided. But then when we go through it, we take Tmin, which is the peak of the completeness over time ratio at like all possible allocation times, and then you start with that time, delegate a delta T to it, and then keep distributing the delta T's that way.
Okay,
Yeah.
so you did not put a restriction on a single star's maximum integration time?
No, we did not.
Okay, Great. And I also really appreciate your wanting to try out changing one of the parameters and seeing what happens there. And the list of questions that you had at the end of all the things that you wanted to try and do with your yield code are exactly the kinds of questions that we want to do with yield codes. They're exactly the things that we're trying to learn about. Thank you.
Thank you.
Good afternoon, everybody. My name is Denise Valadez, a second-year PhD student at Purdue University.
Hi, everyone. My name is Zara Ahmed. Crystal Kim, fourth year at UC Santa Barbara.
Sandrine Drior, PhD student at University of Liège.
Maria Vincent, fourth year PhD student at IFA Hawaii.
And we will be presenting our results on our group project 3B observing schedule. Sorry. So just as a brief overview, what is exoplanet yield? Oh, why is it? My bad. Just as a brief overview, what is exoplanet yield modeling? So drawing inspiration from Christopher Stark's talk on Wednesday, the method of calculating exoplanet yield came out of necessity. And exoplanet yield modeling itself is a way of predicting how many exoplanets are likely to be detected around their respective hosts for a given mission. And it is essential for instrument design. And the reason why it is essential is because it can guide the way that we plan missions and the way that we plan surveys themselves. So what goes into these yield calculators? There are a few subcategories that go into these yield calculators, which can help give the yield calculators more accuracy. So we have things like the astrophysical assumptions. So that could be things like the star model, the planet model, or the stellar catalog itself. We have things like the observational requirements themselves, and then the mission description, which could be the mission duration time itself, or the design of the telescope itself. So, oh my gosh, I don't know why I keep doing that. And so going a little bit further into so these are the inputs, and then that goes into the yield calculator, and the two main components of the yield calculator itself are the completeness calculator and the exposure time calculator, where the completeness is just the probability or the likeliness of detecting a planet. And so when you combine the completeness calculator and the exposure time calculator, you get optimization, right? So you're optimizing it by combining the completeness and the exposure time. So the problem that my group and I were facing was constructing an observing schedule. So what we wanted to do is we wanted to schedule a set of planned observations, taking into account the keep-out map of the observatory and things like the number of targets, the mission duration of 5 years, and also utilizing the keep-out map of the Habitable Worlds Observatory. And our results were as follows.
So we approached this problem, we had a three-pronged approach to this problem. Very convenient, it was three. The first one was where we prioritized completeness as our preliminary requirement. So at a given time, let's call it TN, we found what targets were available to observe, that is what was not in the keep-out region. And then we observed the target with the highest completion, and then we added the integration time, which is T obs, to that start time. And then, yeah, we repeated the same procedure, and as we went through the loop, we also made sure to take out the target that we already observed. And the total time that we gave ourselves, as Denise mentioned earlier, was 5 years. So this was the first prong. The second prong was prioritizing which target took the shortest integration time. Time is of essence, time is money. So here in this method, we start with targets that are available at this given time Tn, and then we prioritize the target which is the easiest or shortest to observe. And so again, we did the same thing. We would add that integration time to Tn, and that would set the start time for the next set of targets after removing the target we already observed. and then we repeat the loop.
So in reality, there's many constraints that we want to consider simultaneously if you're trying to design an optimized mission schedule. And so kind of as a first step in that direction, we decided to take those first two approaches, so trying to maximize completeness and minimize observing time, and create a cost function that essentially divides the two. And so then at every time step, we can try to choose the target that is going to maximize the completeness while also being the shortest observing time. So comparing the results for those three, we can look at this chart that looks at the total number of targets observed, the integration time over the 5-year mission, and then also looks at the total completeness and what the expected yield would be for an exo-Earth with a occurrence rate of 0.24. So just 2 quick points to make here is that we can reach the most number of targets with the shortest integration time approach, as you would expect, but really the benefit of looking at optimizing the completeness and minimizing the integration time is that we can reach pretty much the same number of targets, but reduce that integration time and increase our total completeness for the mission.
So we, thought about some other ways that we could optimize this. For lack of time, we didn't implement them, but here are 2 quite simple ones. So the first is the completeness first approach. This means that we schedule observations in order of highest to lowest completeness. This is similar to the first method we had, but it kind of switches the order which we do it. So we don't look through each time step. We go from a reordered list of targets. And so our second possible optimizing problem is to split up some of the longer integration times to fit in more targets. And then in conclusion, there's a lot of things that we could do to enhance this, and this is a subset of a well-known combinatorial optimization problem set. These include vehicle deliveries within specific windows set by customers or shop tasks that need to be scheduled. So there's a lot of ways that this can be done. And in reality, we have a lot more constraints, including engineering and downtime. And then the targets may not necessarily be available for all hours of the day, which we did assume, and certain target groups might be prioritized over others, so they can be rated in that way as well. Yeah, that's it. Thank you.
I appreciate that you guys tried one prioritization scheme and then another and then a third one that was a combination of the previous 2. So you really got to experience, that range. And then I appreciate your summary table of results in which it looks like, you can get the same yield from the last 2 methods, but you have the advantage of using less time with the third method. And the astrophysics users of the telescope appreciate that whenever we can save that. And then the suggestions that you put at the end, these really are some of the constraints that we run into that just increase the fidelity, because it sounds like, in particular, where you're saying, I'm sorry, on the slide previous to this, it sounded like you were running into the fact that you may have a keep-out window, which exists, but you don't have a short enough integration time to squeeze into it to make use of it. So I'm glad to see your innovative solution, which is you just split it up over a different epoch, as well as where you're saying that the schedule is not necessarily filled up in a chronological order. What you're brushing on there is a look ahead in your schedule instead of just what the next step is. So, well done.
I'm noticing. Who's this one? I'm noticing this one's red. I'm going to replace it.
Hi everyone. Our group worked on active wavefront control with electric field conjugation. My name is Jamila Taki, and
Hi everyone, I'm Angie Huerta. I'm a fourth-year grad student at the University of Notre Dame.
Hello all, I'm Jordan Diaz. I'm a second-year PhD student at University of California, Santa Cruz.
Hi, I'm Ruben, first-year PhD student at the University of Bern.
I'm Michael. I'm a first-year PhD student at UC Santa Barbara.
so electric field conjugation is part of a two-step procedure to perform wavefront sensing, and I believe electric field conjugation is the control part of wavefront sensing and control. And I think the primary use of it is to perform phase aberration correction in space-based instruments. So in the first step, the known aberrations are introduced via the deformable mirror to probe the electric field and form an estimate of the electric speckle field. And then in the second step, knowing the forward model or what deformations produce what effect on the electric field, we attempt to solve for the deformable mirror that will correct or conjugate the electric field. So our group worked on this particular technique to perform control electric field conjugation, and not the first part. We assume we had the electric field.
All right, so now that we all have a better idea what electric field conjugation is, going back to our main question, which is how can we use it for active wavefront control, we've answered the following two questions. So the first question, we were given the HCPI tutorials using that. So for a system with only one deformable mirror, what is the final contrast that you can achieve as a function of input aberration, root mean square? And are we able to achieve a deep contrast if we have larger aberrations? So we have some, let's see if they play. No, not even show the image, maybe?
With the computer, yeah.
Yeah, let's do that. Oh, maybe not. Just a second, y'all. Great, okay. So as I just said, the main thing that we started moving was the aberration amplitude. So the way that we found this first iteration was using 2%, the aberration amplitude was 2% of the wavelength. So we had, I believe it's 14 nanometers. And the main question was looking at the average contrast. So if you can see in this bottom plot here, we can see that the average contrast plateaus at about 10 to the negative 10. And then after this, we started cranking up the aberration amplitude. So the first thing we did was double it, and we shall see another figure, maybe, in a second. All right, we'll see it in a second. But as we double the aberration amplitude, you can see that our average contrast is now 1 order of magnitude less. And we assume this trend to continue on, but we had some more interesting results towards the end as we kept on continuing up, which Ruben will show and explain.
Yeah, so basically we doubled it yet again. So the aberration amplitude is doubled yet again, and then as you will see in this animation, the contrast level will move up even further. So now we're even above 10 to the minus 9 here. So it gets continuously worse. And almost doubling it yet again, not quite. we basically get a very interesting result here. So as you will see, in fact, the contrast levels will go down at first, but then kind of start moving back up. So what's happening here is basically the amplitude of the aberration is now large enough to kind of break through the linearity, kind of break through the linear approximation that the EFC does, and kind of the aberration kind of shines through, kind of leaks through the EFC process, and the, as you can see, the contrast levels go back up.
Okay, so that was the first part of the problem, the project, the first question. Now we'll move on to the second question, which is change the code so that it works with a vortex coronagraph. And when we implement we'll go back to the initial conditions. We'll make the aberrations small again, so that it works right as the first image movie that we showed. And I'll just skip that part and move on to the implementation of the vortex coronagraph. So I tried that using a vortex coronagraph with a charge 2. This is what it looks like. And when we implement the vortex coronagraph, we have something like this. Just in a few seconds. So what happens when we have a vortex coronagraph? You can see that it tricks us, telling us that it will reach a minimum, it will decrease the average contrast, but it reaches a minimum and then it starts to deteriorate. It degrades, and the performance, instead of improving, it degrades. So this is with a vortex coronagraph with a charge equal to, but what happens if we change that to a charge 6? Remember, this is what it looks like. The phase map of the amplitudes, and this is what we get when we have a higher charge. It improves. Now we don't have this turnover. It doesn't reach a minimum and then goes back, degrades. So, but what's causing this? Okay. To answer that, we may want to go back to a notebook that we did work on Monday and look at this figure. Recall that the charge of the vortex coronagraph will perform different to the aberrations. We have how the effectiveness of the charge of the vortex coronagraph as a function of different Sonic-key aberrations. So we remember that for where's the thing? Okay, yeah. So for a small charge value equal to, it is good against low order aberrations, but the higher order modes are leaked. So the aberrations, the light from those aberrations is to passing through. Whereas for a charge 6, it is more robust. It works better against higher order modes of aberrations. So those aberrations, when we move on to a charge 6, are not fed back into the feedback loop of the EFC. Whereas for low order, these higher order modes are passed through still through the loop, and they start to be amplified, and that slowly deteriorates the contrast because those aberrations are being amplified, and instead of being corrected, they start degrading the contrast of the vortex coronagraph of the EFC.
Yeah, so just quick summary. We simulated EFC where the electric field was not sensed. It was just given to us it was just computed directly. by the simulation, and we showed we were able to dig a nice nice dark hole. But for large aberrations, the assumptions made when inverting the DM influence matrix break down, and we get these instabilities, and our contrast degrades. Thanks so much. Okay.
It's okay. Yeah, this is good. Yeah, great. I think you guys actually hit all the important parts that I wanted to show with this group project. Maybe a question that I could ask you is, what would be a way to solve the issue of having a mismatching Jacobian? Because now was the Jacobian calculated in the code?
Well, so we propagated through the optical model the effect of, say, moving each actuator on the DM, and then we inverted that. Then we inverted that matrix. So I guess we could keep only like the lower order terms in the inversion to make it more stable. Is that what?
Yeah, that's an option.
Okay.
Another option is also at every control iteration is to recalculate your Jacobian, so that you actually every time you make a better approximation of the state of your system.
Okay.
But that takes a long while, so it's a trade-off between computation, like time and control. Thank you.
Are you saying to do something like that you use the previous iteration Jacobian as like a prior that you update at each step?
Yeah, that is also something that is currently research, if you could do things like that, where you constantly change your Jacobian of the DM. Because it depends actually, like the Jacobian of the DM depends on the shape that the DM has.
Cool.
Okay. Thank you. I think we need to go. Continue.
I know, we could talk all day.
Hello everyone, I'm Hania. I'm a rising second-year grad student at The Ohio State.
Hello everyone, my name is Rodrigo. I'm currently a first-year PhD student at Northwestern.
Hi, my name is Andy James. I'm from the University of Exeter in the UK.
Hi, I'm El Bogad. I'm a fourth year at the University of Maryland in College Park.
And I'm Arjun Muralidhar. I'm a first-year grad student at The Ohio State University. We worked in estimating mass for the HR 8799 planets using evolutionary models. So I'll quickly go over what we did. Please ignore the numbering of the bullet points. Everything ended up being 1. So we started with our science images, and we used CLIP to subtract stellar PSF. We then injected a total of 12 synthetic planets to measure algorithmic throughput. We experimented with varying the number of synthetic planets we inject at any point of time, and we measured the differences in algorithmic throughput for each of these cases. We then used this to calculate our calibrated flux ratios, and then we used the flux ratio, and we used 2 different evolutionary models to calculate the masses of all our planets. So this is an animation that illustrates our synthetic planet injection algorithm, and I promise we haven't ripped this off from the slides of group 2. We just happened to come up with the same idea. So here we've injected 2 planets at a time at the separation of planet D, and we have varied the position angle to sample the entire radius. We have tabulated results here, and we used a stellar age of 40 million years. We find that for the model for the Ames Dusty model, we estimate a mass that is smaller than the Ames Con model. The Dusty model includes obscuration by dust. And we found literature masses from the NASA Exoplanet Archive, but they have used a stellar age of 60 million years, and therefore there's some discrepancy between our masses and the masses that we found in the literature. We then recalculated our masses assuming an age of 60 million years, and we found that the masses for the Ames Con model sort of are within the bounds of the literature model.
Yeah, so one of the other things we were really interested in was Jason's warning about please do not inject too many planets at once. So what we did was let's inject too many planets at once and see what happens. And so we did a range in sort of orders of two-ish from 1 to 32 planets at a time to see what happens if you really try to cut corners like that. And what we have here is for each of the planets, what is the measured algorithm throughput as a result of looking at, X number of injected planets at a time. And in general, you can see that as you increase the number of planets you inject, the self-subtraction increases, and thus you measure a lower throughput at a given separation. So we have the planets in order of separation, which kind of shows you that algorithm throughput as a function of separation. Unclear as to why planet E did not want to exist after 8 injected planets, but you only have so much time to do these things. But what was particularly interested, because you're not reporting algorithm throughput in your paper, you're reporting your planet flux and converting that to a mass. So this is what happens to your planet fluxes that you might be reporting as you really crowd up that field. So honestly, I thought it was going to be worse than this, but and it's pretty stable, especially for the wider separated planets out to about 8. After that, it gets complicated, but really in your narrow separations, you got to be careful about that. So, lesson learned. Yeah, and I think that's all we have. Thanks so much.
Nice job doing exactly what I told you not to do. Basically, the planets start looking like the PSF halo, so it basically fits, the PCA mode starts subtracting it more efficiently because it looks like a halo. Since you tried this test and you realized that inject more planets becomes unreliable, what would you do in the future to kind of get a more reliable algorithm throughput calculation? You still want lots of planets, right? Because I always say you want to inject more fake planets. How would you go about doing this?
So my guess is you would want to inject them 1 or 2 at a time, measure them individually, and then take the mean at the end.
Yeah. Yes. Yeah. Usually a good idea. Cool. Nice job.
Thanks.
So Jennifer, if you can go ahead and share your screen.
Can you see my screen?
Now we can. So why don't you go ahead?
Can you hear me very well? Okay. Hello, everyone. Very nice to meet you. My name is Jennifer Park, and I'm currently an undergraduate studying at UCR. And before I get started, I just want to mention that because I am an undergraduate, I am no expert in this field. So any advice on what I could improve on at the end would be greatly appreciated.
If you could make sure, sorry, Jennifer, make sure you're close to your mic. You're a little quiet.
Oh, okay. Can you hear me better like this?
A little bit. Maybe speak louder. Go ahead.
Okay. So with that said, how does the contrast curve change when using different imaging subtraction parameters? So these were the original parameters given by the notebook. So we have 11 for annually 1.
We lost her, yeah.
Sorry, I think I got kicked out of the Zoom recording. Hi, does that work?
Okay, go ahead, you're back.
Okay, so these were the original parameters given by the notebook. So we have 11 for annually, 1 for movement, and this array of numbers for numbase. And this is what the graph looks like for the original parameters. And this is the detection map and the SMR map with the original parameters. And right off the bat, you can tell that there are 3 different planets, planet A, B, and C here. The challenge for me then was whether or not we have a 4th planet, and that planet, planet D. And I was basically able to confirm that by adding synthetic data into the algorithm, and I went through the different graphs produced after adding the synthetic data. And basically what this result tells us is that there is a planet D, in fact. If it was not a planet and it was actually an error or noise fluctuation, then the synthetic data graph would not have correctly accounted for that. We can also confirm this further by adding more synthetic planets. On top of that, we are using a 5 sigma confidence level, which basically ensures that the PC for planet D is statistically significant enough for us. Since we are assuming that all the memories within the annually we are using is symmetric with similar properties, that means that our planet noise will be artificially enhanced, what we don't want. So I went ahead and masked all of my planets at these respective units with the guide for the mask. And this is what the graph looks like after the mask. Now to changing movement. When I changed my movement to 0, there was still very at where the planet was supposed to be, despite the fact that I masked all the planets. And that basically indicates that the system is a lot less sensitive to being able to distinguish the planets and the background noise. However, when I started increasing my movement to 2 and to even 3, the contrast graph started to smooth out a lot more, and the peak for the planets actually died down a lot more. And this indicates that the system was a lot more sensitive in being able to distinguish noise from planet noise. So in conclusion, what it effectively did was increasing movement allowed us to basically average out all the pixels in the imaging field more effectively, which helped improve the SNR by reducing the fluctuations. However, by increasing movement, I also was increasing my separation bias. So taking all of that into consideration, my optimal value for movement was 3.25. And this is what the contrast graph looks like, and this is what the residual graph looks like. There were some challenges involved when it came to coming to that value of 3.25, simply because I was not changing any other parameter but movement. I can't just throw in 200 as movement and expect there to be no bias or error within my data. So if I wanted to optimize my contrast graph the best, it would be more optimal to just change all 3 parameters instead of just movement. And that concludes my presentation. Thank you very much for your time.
Hi Jennifer, this is Jason. That was really great work. Especially masking out the planets makes the contrast curve look much more satisfying. So I'm glad someone did that after I hinted at it like 5 times during the hands-on session. So very, very nice. Also, your next steps are totally right on, spot on. Like we want to try to look at how these change with a bunch of the other things. When you looked at your movement parameter, how many different values for movement did you try? Because I noticed you picked 3.25, so that seems pretty precise. So I was wondering how many different values did you try before you settled on 3.25?
A lot.
Very nice.
I spent the last 4 days, like all day, just putting in a bunch of different numbers.
Wow, okay, that's very impressive. Good job. Thank you.
it's just me.
Just you, okay. Forward, back, pointer.
Okay, thank you. Hi, everyone. I'm Arlena Leman. I'm a rising second year at the University of Notre Dame, and on behalf of Group 1A, I will be presenting the project on fast aberrations and adaptive optics. And I'm sure at this point, everybody's back and knees must be hurting, so I will try my best to keep this short and sweet. So the first question we were presented was, which direction do you see the strongest speckles, and what physical parameter do you think influences this direction? So what immediately pops out is that we can see a bit of the spider structures from the telescope. So we were modeling the ELT, and that has these spiders across these directions. And we can also see that there's kind of like this very faint bow tie looking structure. And as for what determines these speckles, there's a few different parameters that affect this, and I'll cover some of them through this presentation. So next we were asked what happens if we increase the wind speed. So in this case, we doubled it to 40 meters per second. And we see that we have some stronger speckles, and that PSF is not as sharp as it was before, so we have worse resolution. And the reason for that could be that a faster wind speed means that your inner scale is varying more quickly across the aperture, and if you can't correct for this quickly enough, then you get worse resolution. Now, what happens if we change the direction of the wind speed so that it's going vertically instead of horizontally? And we see, it's a bit faint, but that bow tie structure that we were previously observing in the horizontal direction, we now can kind of see has been changed to the vertical direction. So the speckles seem to follow the direction of the wind turbulence. Next, we were asked, how do AO parameters such as the gain and number of DM actuators impact the chronographic residuals? So the gain in this context dictates how aggressive your wavefront corrections are. So this was a gain of 0.1. So if your gain is too low, then you could get smoother corrections, but your system isn't able to correct for quicker aberrations, and you get pretty poor corrections. And if your gain is too high, you can initially get faster corrections, but in the long term, if your corrections are too aggressive, then you could end up overcorrecting, and it leads to the cycle of like you're introducing more aberrations, so you fall into the cycle of overcorrection and correcting for those overcorrections, and it's not good in the long term. So you want to balance high gain versus lower gain. And I don't have an animation for it, but the number of actuators can increase your spatial resolution that you can correct for, but if you're not compensating your deformable mirror size, if your actuators are too close together, then that leads to a broader influence function, and that isn't good as well. As for the wavelength behavior, basically the main takeaway is that there's a lambda over d relation for a lot of these things. So a longer wavelength gives you better corrections compared to shorter wavelengths, but shorter wavelengths, you see the turbulence isn't as bad, so there's like a trade-off between those two. And then I'm not completely sure if I implemented this correctly, so I don't know if these animations will show what they're supposed to, but basically the charge of the coronagraph kind of, as we learned on Monday, dictates your inner working angle. So a higher charge gives you a larger inner working angle, so you can get a better starlight suppression, but you won't be able to see planets that are much closer to the star, whereas with a lower vortex charge, you'll have a smaller working angle, so you can see planets closer, but your starlight suppression won't be as effective. So there's a trade-off between those as well. So basically, the takeaway is there's a trade-off between all of these different parameters that can affect your adaptive optics system, and I forgot to include a conclusion slide, but that pretty much concludes my presentation.
Okay, thank you for your work. It's great. I think you essentially explained all the effects that you can see in an AO system. I think the main thing that I wanted to show for your group to investigate is that if you go to an EOT like Aperture and use a classic Leo chronograph or vortex chronograph, you can see that there's a residual diffraction structure because it's not suited to the aperture of the EOT. Did you see that, or do you see structure in the images that look like that?
We didn't quite get to investigate the chronograph effects that much.
Okay, no worries. Great, thanks.
Thank you.
Thank you.